So this video is a problem session based on the material that was covered in week 3 and week 4 of this course. As usual, it's meant to supplement the problems that were given in your assignments, and I hope that you have worked on the assignment problems. So let's begin by checking for whether the following maps, which I'll be writing down in a moment, are linear maps or not. So problem 1. Check whether the following maps are linear. So the first one is a map from R3 to R3 given by, write it down below, T of x, y, z is equal to x plus z, 2x plus y, 3x plus y plus z. The second map that we will be considering is a map T from P2 of R to P3 of R given by T of, say, P of x. This is equal to x times P of x plus P prime of x. Okay, so let's check whether the two maps given here are linear. So checking for a given map, checking for whether a given map is linear or not is quite straightforward if you recall the simpler condition that we had found for checking such cases. So let me just recall that for you. So solution. So solution. So recall that a function f or a function t from v to w is a linear transformation if t of v1 plus cv2 is t of v1 plus c times tv2, where v1 and v2 are in capital V and c is a scalar. So recall that t from capital V to w is a linear transformation. This is the compact condition that we had found. If t of v1 plus cv2 is equal to t of v1 ct of v2 for all v1, v2 in capital V and c in f in R, the scalars. So we will apply this to check, apply this particular proposition we had proved in week 3 to check whether our given maps are linear or not. So for the first one, so what was the map? T was from R3 to R3, where T of x, y, z was equal to x plus z, 2x plus y, and 3x plus y plus z. Let's just go back and check if I have written it correct. X plus z, 2x plus y, 3x plus y plus z. Yes. All right. So let's take two vectors in R3 and a scalar. So let x1, y1, z1, comma x2, y2, and z2 be two elements in R3. And suppose C is in the field of scalars, a real number. And what is V1 plus CV2 in our case? This is just going to be x1, y1, z1 plus C times x2, y2, z2 is equal to x1 plus cx2, y1 plus cy2, z1 plus cz2. So hence T of x1, y1 and z1 plus c times x2, y2, z2 to this by this observation is just equal to T of x1 plus cx2 comma y1 plus cy2 plus z1 plus cz2. But then what is our definition of T? T of xyz is, let me just show it to you. It's written just above. It's x plus z, 2x plus y, and 3x plus y plus z. So here x plus z will just turn out to be equal to x1 plus cx2 plus z1 plus cz2. That is the first coordinate. And the second coordinate was, notice it's 2x plus y. So that is going to be equal to 2 times x1 plus cx2, which is our element, which is our x coordinate here, plus y1 plus cy2. And finally, this is going to be the third coordinate, which is 3x plus y plus z here. So 3 times x1 plus cx2 plus y1 plus cy2 plus z1 plus cz2. This is C. Okay, let's split it and write it down. So this is just going to be x1 plus z1 plus c times x2 plus z2. That's the first coordinate. And then the second one will be 2x1 plus y1 plus c times 2x2 plus y2. And the third coordinate is just 3x1 plus y1 plus z1. These are all real numbers, right? So we can do all these manipulations freely, plus c times 3x2 plus y2 plus z2. Now, if you look at this particular vector in R3, I may as well be able to write it as x1 plus z1, 2x1 plus y1, 3x1 plus y1 plus z1. This is one vector plus c times x2 plus y2, 2x2 plus y2, 3x2 plus y2 plus z2, which is nothing but T of x1, y1, z1 plus c times T of x2, y2, z2. And that establishes that the given map T is a linear transformation. Okay, so let's now look at the second problem. The second problem is telling us that T of p of x is x times p of x plus p prime of x, the derivative of p. That is the second term featuring here. And it is from p3 to itself, or rather p2 to p3 of x rather. Okay, so let's look at the second problem. T from p2 of x, or rather p2 of r to p3 of r, this is given by T of p of x is equal to x times p of x. Notice that this raises the degree by 1 plus p prime of x. Is it minus p prime of x? It's plus p prime x plus p prime of x. So we'll do the same trick as above. Let p1, p2 be two polynomials of degree less than or equal to 2. And suppose C be a real number, an element from the field of scalars. What is T of P1 plus CP2? This is equal to, by the very definition, this is going to be x times P1 of x plus C times P2 of x. So maybe I'll just not bother writing of x, but that's understood. Or maybe let me just write it down. P1 of x plus C times P2 of x plus p1 of x plus c times p2 of x, the derivative of this particular polynomial. But we know that this derivative behaves well. If you look at the derivative of the sum of two polynomials, this is going to be equal to, so let me just write it like this, c times x p2 of x plus This is p1 prime of x plus c times p2 prime of x. But a constant times polynomial, if you differentiate, it is just the constant times the derivative. So this is c times p2 prime of x. And let's now regroup as earlier. So this is x of p1 of x plus p1 prime of x, which is basically t p1 of x plus c times x p2 of x plus p2 prime of x. This is nothing but t of p1 plus c times t of p2, thus establishing that both the examples that we considered were linear transformations. Okay, the next problem is quite similar. It's a problem which tries to find the necessary and sufficient condition for a given map to be a linear transformation, a very particular map. So let's see what the problem is. Problem 2, suppose A and B are scalars such that, and let's now define map T from P of R to R2. Recall that P of R is the vector space of all polynomials with coefficients in real numbers. So T is a map from P of R to R2. As of now, we are just defining a function given by T of P is, so remember, P is a polynomial. So this is just going to be equal to 3 times the evaluation of P at 4 plus 5 times P prime of 6 plus P of 1, maybe 8 times P of 1 into P of 2. This is the first coordinate in the image. And how about the second one? The second one is the integral minus 1 to 2 x cube P of x dx plus b times sine of P of 0. So notice that whatever I have just underlined is a real number. If you look at all the products and sums, it's just going to give us back some real number. Similarly, this will also turn out to be a real number. So indeed, this is a map from P of R into R2. Now the question is this particular map T a linear transformation? So, or rather, it is to prove that, the problem is to prove that T is a linear transformation if and only if A is equal to B is equal to 0. Okay, so let's give a proof of this. So let me just try to keep this particular. Okay, so proving this particular problem has two sides. One is when A is equal to 0 and B is equal to 0, we have to show that T is a linear transformation. That's quite straightforward. Let me not spend time, or maybe I can do it first. It will take almost no time to check that. If A is equal to B is equal to 0, then let's see what happens. Then T of P of x, this will be equal to, let's keep this here so that formula can be taken easily. This is going to be 3 times P of 4 plus 5 times P prime of 6. The B is 0 and hence there will be no extra term, and the next one will be x square P of x dx. This is exactly what our T will turn out to be equal to. So let's look at what is T of P1 plus Cp2. That is just going to be equal to 3 times P1 of 4 plus C times P2 of 4. Again, derivative we have checked, splits, and this is going to be P1 prime of 6 plus C times p2 prime, again this is into, there is a bracket, big bracket here, of 6, that is the first term, and the second term is just going to be p1 plus cp2 of x dx, and splitting and taking advantage of the vector addition that we know, this is just 3p1 of 4 plus 5p1 prime of 6 comma integral of x square of p1 plus cp2 is just going to be equal to, so let me just write that down here in green, this is just going to be equal to integral of x square p1 plus c times x square p2 dx, which is equal to integral of x square p1 dx plus c times integral of x square p2 dx. And that helps us in writing this as p1 of x dx plus the c now can be pulled out in common, 3 times p2 of 4, 5 times p2 prime of 6 plus integral minus 1 to 2, yeah, all those are minus 1 to 2, p x square times p2 of x dx, and we are done because this is equal to t of p1 and this is t of p2. So yes, if b is equal to a is equal to 0, then t is trivially, not trivially, but yeah, after these computations it is a linear transformation. The problem arises, or rather the more difficult side comes in the forward direction, wherein if you have the assumption that T is a linear transformation, we want to prove that A is equal to B is equal to 0. So in order to do that, let's do one thing. So if T is a linear transformation, what do we know? If it's a linear transformation, we know that T of it is additive. T of P1 plus P2 is T of P1 plus P2, right? For all P1, P2. Then T of P1 plus P2 minus T of P1 minus T of P2 is equal to 0 for all P1 comma P2 in P of R. For all polynomials, the additive property is getting satisfied. Similarly, the scalar property is satisfied. Let's focus on the additive property itself. What is this going to manifest as? In the definition that we have, this is just going to be equal to 3 times P1 of 4 plus P2 of 4 plus 5 times P1 prime of 6 plus P2 prime of 6 plus A times P1 plus P2. So P1 of 1 plus P2 of 1 into P1 of 2 plus P2 of 2. If I am to write it down, or maybe this is just the first one, I have to write the second variable as well. That's just straightforward. That's going to be x square times P1 plus P2 dx plus b times sine of P1 of 0 plus P2 of 0. So this will be the value of T of P1 plus P2. Now let's look at what is the other two. The minus T of P1, we know what it is. That is already given to us. That is P1 of 4, 5 P1 prime of 6. So that's a plus. Plus A times P1 of 1, P1 of 2, comma, integral of x square P1 of x dx plus B times sine P1 of 0. And there's one more term, which is T of P2, which will be very similar. P2 of 4 plus 5 P2 prime of 6 plus A times P2 of 1, P2 of 2 and x square P2 of x dx plus P sine P2 of 0. That's it. That's what this is the big expression that we are dealing with. Okay, so let me now put boxes. So the 3 times this term will cancel off with this and this. Okay, let me now use a different color. This term cancels off with this term and this term. We'll come to what is written here separately. This will cancel. Okay, maybe I should use a different color. The red can be used to represent this, cancels off with this plus this, and there is a minus. If you notice, there is a minus here. So all these will cancel off. So let's just write down what is left. What is left will be, after further cancellations, which I will allow you to check, there will be a P1, P1 of 1, P1 of 2 is going to get cancelled. So what will remain is A times P1 of 1, P2 of 2 plus P2 of 1, P1 of 2. That will be the only term which is left in the first coordinate. And what about the second one? B times sine of P1 of 0 plus P2 of 0 minus B times sine of P1 of 0 minus B of sine of P2 of 0. So what was our demand? Our demand was that this is equal to 0 for all choices of P1 and P2. So this should be equal to 0, 0 for all P1, P2 in P of R. Only if this happens will T be a linear transformation. But notice, if, for example, if P, let's pick something, P1 to be the polynomial identically equal to maybe pi by 2 and P2 of x to be identically equal to minus of pi by 4. If you think about what will happen here, okay, let's focus on what will happen. This will give you, then this implies star, let me put star. Star is equal to, maybe the first term will be what? Pi square by 8 into 2, so by 4, minus of pi square by 4, and the second term will be, there will be an a, obviously, there will be a b times sine of pi by 2 minus pi by 4 is pi by 4, which is 1 by root 2, 1 by root 2 minus P1 is pi by 2, which is 1, which is again subtracted by maybe plus 1 by root 2. So something like this. And this is equal to 0, 0 only if, notice, this is only equal to 0 if A is equal to 0 and B is equal to 0. Only if this happens will this be equal to 0 for this particular choice of P1, P2, and hence this forces what we were trying to prove. Hence T is additive, and in particular a linear transformation only if A is equal to B is equal to 0. Okay, so the next problem deals with calculating the value of a linear transformation at a vector if the value of t at specific vectors are given to you. So let's just write down the problem and look at it more carefully. So if t from say R3 to R2 is a linear transformation such that we know the value of t at certain points, such that t of say 1, 0, 3 is equal to 1, 6, and t of 1, 2, 0 is equal to minus of 1 comma 0. So at 103 we know that it is mapped to 1 comma 6, and 120 is mapped to say minus 1 comma 0. Then the problem demands that we calculate the value. Then what is T of 549? This is what is expected. Okay, so what is the only information that is given to us? The only information that is given to us is that T is a linear transformation. We don't know anything else about the map T, right? So maybe let's look at a solution and see how to go about proving this problem or solving this problem. So the only thing that we know is that our given linear map is a linear transformation, nothing else. So in other words, we will be forcing ourselves to use just that simple property to get hold of 549. So to do that, notice 549 is kind of special. So if this is equal to say A times 103 plus B times 120, suppose we can write it like this, then what is T of 549? T of 549 will just turn out to be equal to A times T of 103 plus B times T of 120. Both of these values we know, and therefore let's see what is A and B. If we can find A and B, then we are through, right? So if 549 is equal to, or let me write it like this, it's already written down, so let's call this star, and star implies 549 is equal to A plus B, 2B, 3A. This implies that 3A is 9, which implies A is equal to 3, and 2B is 4, which implies B is equal to 2, and A plus B is 5. So this is a consistent system. Yes, so check that. For A equal to 3 and B equal to 2, 549 is A times 103 plus B times 120. And therefore, we know how to calculate T of 549. Hence, T of 549 is equal to 3 times, what is T of 103? T of 103 we have written is 1 comma 6. 3 times 1 comma 6 plus 2 times this was minus 1 comma 0. What was minus 1 comma 0? T of 120 is minus 1 comma 0. We have just exploited this to write whatever we just wrote below. So if you notice, this is something which we can easily calculate. This is 3 minus 2, 1, 18 plus 0, 18. So this is exactly the value of T of 549. Alright, so we have solved the problem, but let's spend a couple of minutes what we did here to realize what we did here. If you recall, we solved, or rather we proved a theorem which stated that we don't need to define a linear transformation on every vector. If we define the linear transformation on a basis, it automatically extends to a linear transformation on V. In other words, if V1, V2 up to Vn is a basis, and if we mention what T of V1, T of V2 and T of Vn, these n vectors are, then T of V has been fixed for every V. But here notice that we are in R3. R3 has dimension 3, and therefore any basis should have 3 vectors. But here we have only considered the value of T at 2 points, namely 103 and 120. We know that 2 vectors cannot be a spanning set in R3. So what have we done here? So what we have done here is we have considered the subspace generated by 103 and 120. Let's call that say W. And we checked whether 549 is in the span of this or is in W. Then we looked at T restricted to W, and we now know that 103 and 120, we should check that they are linearly independent, and then hence they form a basis. Therefore, this map is exactly like we had defined in the usual case where we define them on the basis and it extends to every vector in the vector space. So yes, so this is a special case applied to a subspace, and T is restricted to a subspace. Okay, so the next problem is an application of the classical dimension theorem which we have proved. All right, so this is problem 4. So prove that if T from R4 to R2 is a linear transformation such that we know what its null space is, such that the null space of T is the set of all, say, x1, x2, x3, x4, such that x1 is equal to 5x2 and say x3 is equal to 7x4. Then prove that T is surjective. So notice that we don't even know explicitly what T is, and yet we are able to say something about the surjectivity of the linear transformation. That's at least that's what the problem demands us to prove here or establish here. So let's give a proof of this. So in order to do that, let me initially invoke and remind you what the dimension theorem is. By the dimension theorem, what is the domain of T? Dimension of the domain, which is R4, this is equal to the dimension of the null space of T plus the dimension of the range of T. And we know exactly what is the left hand side. R4 has dimension 4. Now let's look at what is the null space of T that is given to us. So the null space of T, this is the set of all x1, x2, x3, x4 such that x1 is equal to 5x2 and x3 is equal to 7x4. So I'll not elaborate on this. I will just say that check that from whatever we have seen in the first 2 weeks, check that B, which is given by, what will it be? Let's say 5, 1, 0, 0 and 0, 0, 7, 1 will turn out to be a basis. So you should check this out. I can look at one can look at the expressions here and guess what would be the basis. I know that it should be surjective and hence I know that this is going to be a basis. So it's your job to go back and check that this is indeed a basis. But this implies that dimension of, so this is a check for you. This implies that the dimension of null of T is equal to 2. What does it mean for the dimension of null of T to be equal to 2? This will turn out to be equal to 2 in that case, right? So now what happens to star? Then by star 4 is equal to 2 plus dimension of R of T. In other words, dimension of R of T is equal to 2. Okay, but where is R of T? Notice that R of T is a subset of R2. In fact, it's a subspace of R2. Since, since R of T is a subspace of R2, which is a dimension 2 vector space of dimension 2 itself, what is forced? Then R of T is equal to R2, because if we have a subspace which has dimension equal to the dimension of the vector space, then the subspace is necessarily equal to the vector space. But this is precisely what we mean by saying that T is surjective. That's what we had set out to prove. Okay, the next problem, let me call it 5. Problem 5, it states the following. So this is again I prove that something exists. So suppose V is a finite dimensional vector space and T from V to W be a linear transformation. Prove that there exists a subspace U of V such that U intersected with null space of T is equal to the 0 set and such that and R of T is equal to Tu for U in capital U. So if you are to recall the concept of an isomorphism, what this says is that there is a subspace U of V such that when T is restricted to U, it is an isomorphism onto the range of T. So in particular, if T is a surjective map, then what this problem essentially says is that there exists a subspace U of V such that when T is restricted to U as a map from U to W, it is an isomorphism. Okay, that comes later. Let's first prove the problem, prove the existence of such a subspace U. Okay. All right. So in order to prove the existence of such a subspace, let's focus instead on the range space of T. So since V is finite dimensional, so notice that in the problem there is no assumption on the finite dimensionality of W. So we don't need W to be finite dimensional to establish something of this sort. So since V is finite dimensional, however, this forces by the dimension theorem dimension of R of T, which is dimension of V minus the dimension of null space of T, is finite. This is a finite dimensional vector space, subspace of W. So let's say N is the dimension of R of T. And what does it mean to say that N is the dimension? There is a basis. There are bases of R of T of size N. And beta be the one such basis, W1 to Wn be a basis of R of T. But what do we know about R of T? R of T is precisely the range of T. So in other words, every Wi is the image of some vector Vi. So let Vj rather be vectors in capital V such that Tvj is equal to Wj. Now let alpha be equal to, or rather let U be equal to the span of all these V1, V2 up to Vn. My claim is U is the required subspace. So when I say the required subspace, what does it mean? Let me just take you back to the statement of the problem. The problem says that, underline it in green, there exists a subspace U such that U intersected with the null space of T is 0 and R of T is exactly equal to this. Okay, so let's give a proof of this claim and establish it. So the first part is to show that U intersected with the null space of T is 0. This is what the question mark is, right? So let V be in the intersection of U and the null space of T. So V is an element of capital U implies that V is equal to some A1 V1 plus up to AN Vn, because recall that capital U is the span of V1 V2 up to Vn. Then what is T of V? T of V is 0. Okay, and T of V is 0 because it is in the null space. But what is T of V? T of V is A1 TV1 plus up to AN TVN, the standard trick which we have been using so many times. This is equal to A1 W1 plus up to AN WN. And what do we know now? This is equal to 0. And we had started off with W1, W2 up to Wn, which are basis elements of R of T. And therefore they're linearly independent. So I'm not writing any of these things down. I'm just writing that Aj is equal to 0 for all j, which implies V is equal to 0. So this implies, so we see, we started off with an arbitrary vector V in U intersected with the null space of T, and we have proved that it is supposed to be 0. 0 is obviously in the intersection of both because both are subspaces. So hence the intersection is equal to the 0 subspace. And what else is left to be seen? R of T. So let W be some, so let to show the second part wherein we have to, what was the second part? It was to show that R of T is exactly TU for U in capital U. I'm just underlining that in green right now. This is what we are going to prove. So let's take some arbitrary vector W in R of T. We know that W is equal to A1, we have used A1 already, B1 W1 plus up to say Bn Wn for some scalars B1 B2 up to Bn, which is equal to B1 of TV1 plus up to Bn of TVn, which is equal to T of B1 V1 plus up to Bn Vn, which is an element of capital U. So which is equal to TU for U in capital U. That's precisely what we had set out to prove. So yes, we have established this. Now it's a good task for you to sit down and check that T restricted to U. We have done all the work already. You have to just check that T restricted to U is an isomorphism, is an invertible linear transformation from U to R of T. It's not a part of this problem, but it's a worthwhile exercise for you to sit and think about. Okay, let's now look at one more application of the dimension theorem. So this is problem 6, I guess. Yes, problem 6. So problem 6. So let V1, V2, V3 and V4 be vector spaces such that dimension of V1 is equal to 8, dimension of V2 is equal to 5, dimension of V3 is equal to 7, and dimension of V4 is equal to 6. So we are given 4 vector spaces V1, V2, V3 and V4. The dimensions of these are 8, 5, 7 and 6. Now let's consider linear transformation. So let T1 from V1 to V2, T2 from V2 to V3 and T3 from V3 to V4 be linear transformations. and let's call the composition and let T be equal to, so let me be careful with the T1, T2, T3. Right, so T be the linear transformation T1, T2, T3. So we have seen that composition of linear transformations is again a linear transformation. So in particular, T is a linear transformation. Okay, the problem is to prove that T is not surjective. So if you notice, we have absolutely no information about the specifics of T1, T2 or T3. They are some linear transformations. In fact, any linear transformation from V1 to V2, you consider call it T1, consider some other linear transformation T2 from V2 to V3 and so on. And you look at the composition, whatever be those linear transformations, this problem tells us that it cannot be a surjective linear transformation. So let's give a proof of this statement. Okay, so what does it mean for some map to be surjective? It means that the range space is equal to the domain. So T is not surjective if R of T is a proper subspace. But if it is a proper subspace, the dimension will be smaller, right? And only if the dimension is smaller will it be a proper subspace. Enough to show, so hence, yeah, enough to show that R of T, the dimension of R of T is strictly less than the dimension of, what is the image of V4 is the image of T, right? What is the image of T? V4. And this is having some dimension. What is the dimension of V4? That is being given here to be 6, as you can see here. So if we show that this is less than 6, if the dimension of R of T is less than 6, then we are done, because it cannot be a proper subspace which has dimension equal to 6, right? Yeah, so let's not try to prove that the dimension of R of T is less than 6. But what is T? Recall that T is nothing but T3, T2, T1. And so let me make a claim. R of T is contained in R of T3, T2. So that's not a difficult claim to prove. So if, say, for example, W belongs to R of T, this means that there exists V in capital V1 such that TV is equal to W. But that means T3, T2, T1V is equal to W. Let's call T1V something. Let T1V be equal to, say, U, then W is equal to T3, T2U. This implies that W is in R of T2, T3. So yes, so certainly R of T is contained in R of, T3, T2. T3, T2. So now let's focus on T3, T2 now. What is T3, T2? T3, T2 is a map from, let's see, V2 to V4. And the dimension theorem tells us that dimension of V2 is equal to the dimension of the null space of T3, T2 plus the dimension of the range space of T3, T2. Or to put it in another way, dimension of the range space of T3, T2 is equal to the dimension of V2 minus the dimension of the null space of T3, T2. In other words, the dimension of the range space of T3, T2 has to be strictly not strictly, less than or equal to the dimension of V2. What is dimension of V2? Let me go back and show what the dimension of V2 for you is. Let me box it in green. It's equal to 5. So what we have established here is that dimension of the range space of T3, T2 is less than or equal to 5. But we just showed that R of T is contained in R of T3, T2. This implies dimension of R of T is less than or equal to the dimension of R of T3, T2, which is less than or equal to 5, which is less than 6. And therefore, it cannot be surjective. This is exactly what we had set out. So, in the setup which we had just described, there cannot be linear transformations such that if you compose it, it will turn out to be a surjective map. Okay, so the next problem is a problem on computing the matrix of a linear transformation corresponding to a given basis. So I'll just do a very straightforward example. This is not a problem which is complicated at all, so let me not spend too much time on it. So let's fix a basis. So let alpha being equal to, say, the following basis of, say, 2 cross 2 matrices. 1. So this be a basis. So let alpha be a basis of M2 cross 2 of R, basically 2 cross 2 matrices over R, and let beta be equal to the set, or rather ordered basis consisting of the constant 1 be an ordered basis. So both are ordered basis. So let me not confuse you by writing it. 1 be an ordered basis here as well, an ordered basis of the vector space R. So here R is being considered as a vector space over itself. So any non-zero element will turn out to be a basis, right? It's a dimension 1 vector space. So what is this problem? This problem asks us to compute the matrix of the following linear transformations. So what is the first one? The first one is T of A. So let me say, this is what we have to compute: alpha, the matrix of T with respect to alpha, where T of A, T, let me just write it. This is the transpose of this matrix. So notice that T is a map from M2 cross 2 of R to M2 cross 2 of R. And what about the second one? The second one is T alpha beta, where T of A is equal to the trace of A. And where is this map from? So this is from 2 cross 2 matrices over R into R. So both, I'll not check that these are linear transformations. I'll just leave that to you to check whether these are linear transformations. Let's jump into computing the matrix of these linear transformations. So let's give a solution. So the first one is the matrix of T with respect to alpha, right? So let's write down what T is. T of A11, A12, A21, A22. This is just going to be equal to A11, A21, A12, A22. This is precisely the transpose of A11 of the matrix which is just written to the left. And to compute the matrix of a linear transformation with respect to a basis, or to basis beta and alpha and beta, we compute T of the basis elements in alpha and write it down in terms of beta. That will turn out to be the coefficients of what we have in terms of beta will turn out to be the column corresponding to the vector which we have picked. So in other words, so recall. So I'm just recalling, or maybe I'll just prove this or find the matrix here and recall the relevant aspects to you. So in order to compute the matrix, so here what will be the matrix? So recall that in this case T alpha alpha is a 4 cross 4 matrix. Right? What will be the first column? So let's see what the first column is. Column 1. Column 1 is look at T of 1 0 0 0 and see what it is in terms of the other matrices, the basis alpha. This is just going to be 1 0 0 0 by definition, which is equal to 1 times 1 0 0 0 plus 0 times 0 1 0 0 plus 0 times 0 0 1 0 plus 0 times 0 0 0 1. Maybe I should write it below. Plus 0 times 0 0 0 1. And hence the first, so let me just capture the matrix for you here. T alpha alpha, the first column will just be these coefficients which I am underlining in green, and therefore this will just turn out to be equal to 1 0 0 0. Okay, how about the second column? Second column will be of corresponding to the second basis vector, which is 0 1 0 0. And if you compute, this is just going to be equal to 0 0 1 0 will be the image of 0 1 0 0, which is equal to 1, which is not equal to 1. This is equal to 0 times 1 0 0 0 plus 0 times 0 1 0 0 plus 1 times 0 0 1 0 plus 0 times 0 0 0 1. Therefore, what will be the second column here? That is just going to be 0 0 1 0 0 0 1 0. How about T of 0 0 1 0? That's just going to be equal to 0 1 0 0. That's just going to be 0 times this plus 1 times this plus 0 times this plus 0 times this, whatever is there above. And from there I'll take you to write this is 0 1 0 0. And the final, let me not write down, the computation is extremely similar, and this is exactly what the matrix of linear transformation T with respect to alpha is going to look like. Okay, so that is the first one. How about the second one? The second one is the trace. So 2 T of A is equal to the trace of A. So let's write it down explicitly and see what it is. This is T of A11, A12, A21, A22. And what is T of A1? This? What is this? This is equal to A11 plus A22. I'll check. I'll not check that this is a linear transformation. I'll leave that to you. Let's, however, find out what the matrix of T will be here. Yet again, we are going to do the same type of calculations. We will compute T on the basis vectors, write it down in terms of the basis vectors in the image, and hence get hold of the columns of the matrix of the linear transformation. So here notice that A is coming from M 2 cross 2 of R, which is a 2 cross 2 matrix, which is a dimension 4 vector space, and the image is a real number in the vector space R, which is dimension 1. So this matrix is going to be a 1 cross 4 matrix. Okay, so let's compute what the matrix will be. So what is T of 1 0 0 0? This is just 1. Similarly, what is T of 0 1 0 0, which is equal to 0, which is the same as T of 0 0 1 0. And what about T of 0, 0, 0, 1? That is also equal to 1. So this matrix is just going to be equal to, from here the first column comes, from here the second and the third column comes, and from here, not write it down like this, it's 1, fourth column comes. So the 1 cross 4 matrix will look like this. Okay, so I did not take more complicated bases because the calculation will just become slightly more complicated. It will not reveal anything more. You just have to take the basis vectors from V, compute what T of those basis vectors is in terms of the basis vectors in W, and that will give you the columns of the linear transformation, matrix of the linear transformation. All right. So the next problem demands that we prove two vector spaces as being isomorphic. So problem 8. So prove that for any vector space V having finite dimension, the vector spaces V and L of V comma F are isomorphic. V and L of, or rather R comma V are isomorphic. So recall that L of V comma W was the space of all linear transformations from V to W. We had proved that that is a vector space. We had also proved that it is isomorphic to the vector space of M cross N matrices over R, where M is the dimension of V, a dimension of W, and N is the dimension of V. So in this case, so this is actually a very straightforward proof. Recall that L of R comma V, which is a vector space of all linear transformations from R to V, this is isomorphic. In fact, let me not write all this. We had shown that it is isomorphic to the matrices of M cross, the vector space of M cross N matrices, and therefore L of V comma W is having dimension equal to dimension of V times dimension of W. So recall that dimension of L of V comma W is equal to the dimension of V times the dimension of W. But in our case, V is just, okay, the role of V is, W is now V in our case, and V is R in our case. So therefore, by this argument, dimension of L of R comma V is equal to the dimension of R times dimension of V, which is equal to the dimension of V. So we know that now the dimension of L of R comma V is the same as dimension of V. But what do we know about vector spaces which have the same dimension? By a theorem we proved in the fourth week, two finite dimensional vector spaces are isomorphic if and only if they have the same dimension. And by invoking this particular dimension, both these vector spaces are isomorphic. So if you notice, we got hold of a proof of this particular problem without doing any effort. We did not get hold of an explicit linear transformation from V to L of R comma V, and we did not bother checking whether it's a linear transformation. In other words, our problem was cut short by the theory that we had developed, and using that we get this particular problem in a jiffy. Excellent. Okay, so let me conclude by finally getting hold of the property of being invertible using the dimension theorem. They are all interconnected to be as to be expected. So this problem asks us to prove that this particular map, let P from Pn of R to Rn plus 1 be the map. So let me not write that it is a linear transformation. That even I will not check. Let me just leave it to you. P of 1 up to P of n. So notice that this is an element in Rn plus 1. So T of P is this. So prove that, of course, you have to prove that T is a linear transformation. Prove that T is a linear transformation and that it is an isomorphism. T is an isomorphism. Okay, so one of the most essential things to establish that it is indeed an isomorphism is to check that it is injective. Now, injective maps. To check that something is injective, what do we need to do? It is injective if and only if the null space is the zero subspace, right? So let's pick some vector. Let P be in the null space of T. What does it mean to say that P is in the null space of T? It means T of P is 0. But what does it mean to say that this is 0? i.e. P of 0 is equal to, all this is 0. P of 0, P of 1 up to P of n. All these are equal to zeros, right? That is precisely what it means for P to be in the null space of T. But P is a polynomial, and by the factorization property, we know that because P of 0 is 0, P of x is equal to x times Q of x, or rather let me write it as Q1 of x. And we know that similarly, x times Q1 of x is, does not satisfy. So observe that this implies Q, since, okay, let me not rush. Since P of 0 is equal to 0. Okay, next. P of 1 equal to 0 implies 1 times Q1 of 1 is equal to 0. This implies P of x is equal to x times x minus 1 times Q2 of x. And continuing like this, we have P of x is equal to x into x minus 1 into up to x minus n times Qn of x. But notice that this polynomial will have degree greater than or equal to n if Qn of x is non-zero, and that will not be an element of Pn of r. So we need this element to be in Pn of r. So if Qn of x is not identically equal to 0, then degree of P of x will be greater than n plus 1, which is a contradiction, since P of x to begin with was an element in Pn of x, n plus 1, which will be greater than or equal to n plus 1. It will be greater than n for sure, which is a contradiction. And therefore, Qn of x is identically equal to 0. This implies that P of x is identically equal to 0. So yes, we have established that the null space of T is just the 0 vector. But then, now we will invoke the dimension theorem to say that dimension of Pn of R is equal to the dimension of the null space of T plus the dimension of R of T. And this we know is 0 because null space is the 0 vector space, which gives dimension of R of T is equal to n plus 1, which is the dimension of Rn plus 1. So we don't need to explicitly check for surjectivity in this particular case, which might have been a complicated thing to do. The dimension theorem directly tells us that because our map is into Rn plus 1, our dimension is known to be n plus 1, and this implies that R of t is equal to Rn plus 1. Hence, T is surjective. What can we say about an injective and surjective linear transformation? Should necessarily be an isomorphism. That is the definition, because it will be invertible, right? Hence, T is an isomorphism. So if you notice, this is an isomorphism which we have defined without going down to any basis.